Hello, and welcome to Group B09's Group Project Video Presentation for AE3340. Our project is titled The Development of a Space Debris Deorbiting CubeSat, a Design Concept Proposal. The members of our group are as follows: Samuel Ball, Daham Aom, Justin Ezekiel, Turner Glenn, Joshua Ingersoll, and Jacob Wallace. So, what exactly is our project? Well, we are proposing to design a 3U-sized CubeSat that has the capability to attach to pieces of debris and knock them out of orbit. This will be accomplished through a combination of a harpoon-based attachment system and an inflatable-based drag induction system. Essentially, our product will act as a parachute for pieces of debris by harnessing the drag force from collisions with the rarefied gases at low Earth orbit. Our CubeSat will help clean up congested orbits and help prevent future collisions. This project is less of a final product and more of a proof of concept for this new deorbiting technology, as it does not currently exist. As such, we will be launching our CubeSat from the ISS using the NanoRacks deployer and deorbiting a nearby piece of debris instead of having a dedicated launch vehicle. This will allow us to keep costs low and show potential buyers that our product is a viable solution for an already known problem. This, of course, is the problem of orbital debris. Orbital debris poses a real threat to any potential space missions, as an impact with it can render any payload useless and create even more debris. It is estimated that there are over 16,000 individual pieces of debris currently orbiting the Earth. Many of these are byproducts of previous missions, such as rocket stages or fairings, but the majority of these pieces are tiny fragments that were caused by satellite collisions. These fragments are the most dangerous category, as many of them are too small to be tracked. These unseen threats can have more energy than a bullet and can rip holes through any material in their path. After witnessing events like the Chinese anti-satellite test and the Cosmos Iridium collision, there is clearly a need to deorbit as much useless mass as possible to decrease the chance of future collisions and future fragmentation. So now that we have defined our problem, how do we plan to solve it? As stated earlier, we will do this through the use of a small 3U-sized CubeSat. This small but powerful satellite will be deployed from the ISS through the NanoRacks system and move towards a targeted piece of debris. It will attach itself to the debris by first activating a group of electromagnets to provide a soft seal, and then secondly with a harpoon that will pierce the debris and provide a permanent seal. Once the attachment system has sent confirmation of success, we will engage an inflatable that will slowly drag the debris out of orbit. It is our group's belief that our solution is novel, as there has been a bit of research in this area, but no successful implementation of this technology. Success of this project would appeal greatly to a number of different potential customers and stakeholders.
The two largest groups of our potential stakeholders and customers are space and defense agencies and private companies that have satellites in orbit. Most of these organizations have inoperable satellites in low Earth orbit for which they are still responsible. Organizations that have functioning satellites in orbit would also probably have an interest in our product, because those satellites will most likely become uncontrollable debris at some point in time. Private companies need to be additionally concerned, because they could be prosecuted over an accident, which could lead to bankruptcy. The need that drove the development of our product is fairly straightforward. The chance of a collision with debris in low Earth orbit is dangerously high and rising, and something must be done to correct this. Our system will aim to resolve this issue by removing derelict satellites from orbit, while also being cost-effective. Removing debris from orbit is currently quite expensive, and it's often not worth the cost. However, that could change with the use of CubeSats, which are relatively cheap and can be put into orbit quickly. Our specific proposed mission is to demonstrate the practicality of our idea by deploying a CubeSat from the International Space Station and deorbiting a nearby piece of debris within a specified time frame. The entire project will be managed and carried out by Georgia Tech students and faculty.
Stage 1 of our concept of operations will be launching the CubeSat aboard a NanoRack storage system. Then Stage 2 will be to dock with the International Space Station. From there, we will move on to Stage 3, which is to separate from the NanoRack deployer. Once we have done that, we will move into Stage 4, where we position and orient the CubeSat next to the targeted debris. Once the CubeSat has been oriented, we will move into Stage 5, where we attach the targeted debris using electromagnets. The electromagnets will secure a connection to the space junk, and then we will move into Stage 6, where we launch a harpoon into the debris to create a permanent connection. Stage 7 will then be to deploy a drag-inducing inflatable to deorbit the debris, and then, after a pre-specified time by the customer, we will eventually burn up in the atmosphere upon re-entry. Here we will discuss our project lifecycle. We have already begun. We are in pre-phase A of our concept studies. By June of this year, 2017, we predict to be in phase A of the concept and technology development. It's in this phase that we will be consulting industry experts to help us solidify the technology needed for the satellite's attachment and drag induction systems. By December of 2017, we predict to be in phase B of the preliminary design and technology completion. It's in this phase that we would have a solid baseline and know much more about the overall cost of the project. By December of 2018, we predict to be in phase C of the final design and fabrication. By September of 2019, we predict to be in phase D, where we assemble the system, vigorously test the system, and finally launch the system. Then in March 2020, we would be in operations and sustainment. And in April of 2020, we would be in phase F of closeout and disposal. And it's in this phase that we will confirm a safe trajectory and allow the satellite and its target to burn upon re-entry.
This is the system hierarchy of our deorbit system. Of course, we begin with our deorbit system at the first level, and then below it at Tier 1 are our CubeSat and launch system segments. Since we are relying on the International Space Station to deploy our CubeSat, our launch system terminates here at the segment level. And here at Tier 2, all the elements of our system stem from the CubeSat itself, and most of these elements are relatively standard for a CubeSat, such as the structure composed of the internal and external structures, and the avionics system containing the communication and instrumentation subsystems. Also, we have the power systems and the gas propulsion system of the CubeSat, again, very standard for this type of spacecraft. The real purpose of this CubeSat lies in our final element, the debris deorbit system, comprised of the attachment and drag devices. The attachment system contains the electromagnets used for initial contact, and also the harpoon needed for a more secure connection to the debris. And lastly, we have the drag system, comprised of the balloon and gas container used to fill the drag balloon, both of which will ultimately cause the deorbit of the attached debris.
The top-level system requirements for the deorbiting CubeSat are as follows. The CubeSat shall comply with all NASA and NanoRacks deployer requirements. The CubeSat shall use an inflatable structure to achieve the deorbit requirement. For time in orbit, the CubeSat shall deorbit the targeted satellite within a 25-year period, a requirement standard for orbital debris mitigation practices. For structure requirements, the CubeSat shall comply with NASA standard practices for CubeSat structures. For the avionics requirement, the communication system for the CubeSat shall receive and send communication signals in range of a targeted Earth orbit during all mission phases, and shall have the capability to receive a transmitted shutdown command as per FCC regulation. The internal system for the CubeSat shall have a sensor confirmation for each system operation, such as but not limited to the propulsion system sensors, attachment system sensors, and drag system sensors.
Use a power system which contains inner battery that satisfies NASA very set requirements and at least 3 mechanical deployment switches. Also, additional power shall be provided by external solar panels. CubeSat gas control system shall maintain optimal thrust in range of 0.125 newtons depends on its propellant. The Orbital Debris system shall contain attachment and drag system. In attachment system, electromagnets shall have the capability to remain attached to target debris with contact surface area greater than 100 square centimeters, and harpoon shall penetrate and adhere to a target debris. In drag system, the total system mass and volume shall not exceed 0.2 kg and 0.9 cubic centimeters. The balloon system shall meet the gold project requirements and shall be inflatable during operations, and gas container shall insufflate gas into the balloon.
We chose a standard mass contingency plan for this project. We set the predicted best estimate to be 35% of the maximum estimated value at the time of the system requirements review, 20% at the preliminary design review, 15% at the critical design review, and 2% at the launch readiness review. We chose a 10% margin for the total mass to provide a buffer in case of unexpected changes during development and design.
Looking on to the future, and assuming our proof of concept mission from the International Space Station is successful, we could apply our deorbit system in a number of different ways. The first of which is deployment in a cluster. By launching a group of our CubeSats into orbit on their own dedicated launch vehicle, we could reduce the potential for collisions and perform multiple deorbit missions along popular Earth orbits.
Finally, one thing we really wanted to address with this project was our potential to upscale. Obviously, there is a wide variety of size of debris in space, and we feel that this project has a good potential to scale to fit that variety. For instance, satellites like the ESA's Envisat are projected to be in orbit for upwards of 100 years, and a larger model of our satellite that we've created could be used to help assist its deorbiting process.
Thank you so much for taking the time to view our presentation.